Morning, everyone. It's Dan Sanding from the Institute for Catastrophic Loss Reduction. Thanks very much for joining us. This morning, we've got Dr. Kelin Wang from the Geological Survey to talk to us about Megathrust earthquakes. It should be a very good presentation. Before we get started, there's a couple of logistical things that we should go through. First, as in all of our webinars, we will take questions throughout the webinar. In order to ask a question, you can scroll to the top left, just move your cursor to the top left of the screen, and a toolbar should drop down that has a Q&A button. If you click that button, the Q&A window will open up, and you can enter your questions in there at any time throughout the webinar, and we'll hold the discussion to the end of the webinar. If you have any questions about that, please feel free to ask using the chat or Q&A options. And before we get started again, we'll remind everyone that we have a number of upcoming presentations, all held by webinar, but you're free to join in our office if you'd like and view the webinar with us, but most of our presenters will be off-site. The next presentation will be from Lynn Johnson from the Canadian Forest Service on February 17th, and Lynn will be talking about her work developing national wildland-urban interface maps. These are the first urban infrastructure and industrial interface maps that have been produced for Canada. So feel free to join. We should be sending a notice out pretty soon for that. And another reminder that we will be posting this presentation and future presentations on our YouTube website. Typically, we do this within a few days following the webinar, so feel free to go to our website and click on the YouTube button, and you'll be able to find the recording of the presentation there. So with that, we have, again, Dr. Kelin Wang from the Canadian Geological Survey. The presentation of the title is Great Cascadia Megathrust Earthquakes, Past, Present, and Future. Dr. Wang is a research scientist with the Geological Survey of Canada. He did his Ph.D. in geophysics at the University of Western Ontario. He's got quite an impressive biography, which I think probably most of you have seen. In 2015, he was awarded the Tuzo Wilson Medal from the Canadian Geophysical Union, and he was named the Birch Lecturer by the American Geophysical Union. So with that, I'll pass it to Dr. Wang.
Thank you, Dan. Yeah, good morning, everyone. Thank you for attending this seminar. As you know, the reason we have the Friday seminar on a Thursday because and today is the 317th anniversary of the Cascadia earthquake. This is a Cascadia subduction zone, and here we have the Tectonophysics plate subducting beneath the North American plate. And on this subduction zone, we have many different types of earthquakes, and we have earthquakes in the ongoing slab, and the most recent big one was 2001. The Nisqually earthquake near Seattle, and we have earthquakes within the upper plate, the continental crust, and such as the 1946 Vancouver Island earthquake, and also with caused a lot of damage. And more recently, we have earthquake further to the north. That's the Hydrogeological earthquake, and the second largest recorded earthquake in Canada. And that was more or less the same plate boundary, but here the mode of plate motion, relative plate motion, is somewhat different. And today, what I will talk about is the largest type of all these earthquakes. That is the earthquake on the interface of the two converging plates. And the last one, as I just said, occurred exactly 317 years ago, and that was the Cascadia Megathrust earthquake with a magnitude about 9. And so let's first put the okay. So all this is of great scientific value and societal importance, but also is to me is a personal matter because this is where I live here. I live in Victoria. So let's first put the whole thing in a global context. And here's the sequence of large earthquakes worldwide over the past century or so. And if you focus on the events greater than magnitude 8, great earthquakes, and we will see, and prior to 2004, and we had about one event of this size every 18 months. But since 2004, and we had one of these events about every 7 months. So this is the busy period. And we don't know whether this is just a coincidence, just a sampling matter, or there's some physical reason. But whatever the reason, it serves to remind us the importance of studying these earthquakes, paying attention to their potential damage, and do good work in mitigating their risk. And one of these two, in this period, one of the two largest, two of the largest events are the giant earthquakes of 2004 in Sumatra and 2011 in Japan, the so-called Tohoku-oki earthquake. And these are the rupture zones of these two events. Both earthquakes caused huge tsunamis and caused a lot of fatality. And the Sumatra earthquake killed 250,000 people, and the Tohoku-oki earthquake caused about 20,000 deaths. And but if to put the whole thing into proper context, let's view the two rupture zones at the same spatial scale. And now you can see the Tohoku-oki earthquake is a lot, actually in terms of rupture size, a lot smaller than the Sumatra earthquake. So it turns out there are different types of giant earthquakes. And these two are the two end members. So I call the first one the Tohoku type, and this is the compact type. It features a pretty small rupture and a short duration, as you can see from here, what we call the source time function. And here the whole thing takes about 2 minutes to complete, but with a huge energy release over a short time. And also it has a huge slip here. See the maximum slip is greater than 50 meters. And the reason we think it's probably because the whole thing is controlled by some local, fairly strong patch of the Megathrust fault. And in contrast, the Sumatra type is more spread out. It has very long rupture, in this case, about 1,300 kilometers. And it has a very long duration. And it took about 9 minutes to complete the rupture because it took time for the rupture to propagate from one end to the other end. And the slip was much smaller. Like the maximum slip here, shown here, is much smaller than that of the Tohoku earthquake. And so for this type of earthquake, and it seems there's not a very strong local patch to cause a compact and a localized rupture. The fault zone seems to be much smoother, and if it ruptures, it goes a long way. So we should keep this in mind when we talk about think about the Cascadia event. In between these two end members, we have seen other earthquakes, such as the 1964 Alaska earthquake, and this one is a bit more like the Tohoku-oki earthquake, but larger and longer duration here, the blue line here, so you can see. And also the world's largest recorded earthquake known to us was the 1960 Chile earthquake with magnitude 9.5. And that one seems to be a mixture of the two, and it features some very large slip locally, but it also it was very long, ruptured, and lasted for a long time. So what about Cascadia? Again, at the same spatial scale, Cascadia rupture looks like this. And this is the most recent rupture model for the earthquake without 300 years ago. And I will come back to it later in the webinar. So we should keep this whole thing in mind when we look at the Cascadia, and to when we study its behavior, and we need to compare it with other subduction zones, other megathrust earthquakes. So how do we know about the Cascadia earthquake? And we had, as you all know, we have a fairly short recorded written history, and so we know about the past earthquakes in different ways. And first, we know about past earthquakes from local coastal geology. To your left-hand side is these cartoons show the subduction zone between earthquakes when the fault is locked here, when it's stuck and accumulating a strain, and the upper plate is being shortened like a spring and accumulating energy. And the bottom part shows when the fault and can no longer hold, it will produce an earthquake, it will rupture to produce an earthquake. At this time, and the coast will subside, and the seafloor will rise and to cause tsunamis. And of course, the picture here is exaggerated by probably at least 1 million times, but you can see what I mean. And the coastal subsidence here, the sudden subsidence, and it's very often recorded by geology. Like to your right-hand side, you see that the peat layer here, that used to be grass, and it was buried suddenly, and because of coastal subsidence, and that was interpreted to be evidence for a coseismic rupture, a subsidence deformation, like shown here to the right left-hand side, and along the Cascadia coast, we have evidence of this type in many places. So this older picture, but we actually have more locations that show this kind of evidence. And also very often, and some of the trees were half killed because of the water came in, and by dating these trees, we could also constrain the approximate time of the sudden coastal subsidence for the earthquake rupture. And frequently, the subsidence is accompanied by tsunami sands, because the earthquakes produce tsunamis, and the waves come in, bring in the sands. And geologists can tell these sands are not locally derived. They came from offshore. So there's strong evidence these are tsunami records. Again, along the Cascadia coast, we have many locations that show this kind of evidence, tsunami sands. Like in this case, on one occasion, and we have tsunami sands on top of a fire pit. So there's evidence for human activity, and that layer, that event was dated geologically to be in this period, but geological dating and has a large uncertainties, was never very precise. And how did we get to know the exact time of the earthquake in 1700 AD? And that actually came from historical records in Japan. And many of you may have already known this story, the story of the 1700 orphan tsunami in Japan. And Japanese people, they are very experienced with tsunami and earthquakes, and they know that tsunamis follow large earthquakes. But this time, and there was this tsunami that caused a lot of damage in different places along the Japanese coast, fairly large tsunami, but was not preceded by an earthquake. And they recorded the damage in different places. They also said in one of the records, this tsunami was not preceded by an earthquake. The source for this tsunami will have to be studied by future generations. Now, the future generations, and by studying the records and by modeling different places, and now we know the tsunami was caused actually by a big earthquake on our coast, the Cascadia earthquake. This is how we know the precise timing of the earthquake quite exactly. And that earthquake occurred on this day, 370 years ago, about 9 o'clock in the evening, local time. So how do we know this earthquake? How often these earthquakes occurred in this subduction zone? We come back to our own subduction zone. We study the offshore turbidites, and sediments will accumulate on the continental shelf and slope. And when the earthquake occurs and causes ground shaking, and the sediment will be shaken loose, and they will flow as turbidites along certain channels and accumulate on the seafloor. And scientists now can take cores from the seafloor using instruments like this, and by studying these cores, and they could identify these turbidite layers and study the timing of these events, and came up with a record of earthquake history. And as shown summarized here, and this is the most recent compilation by Chris Goldzinger et al. And it turned out the Cascadia subduction zone and has a tendency to produce a fairly long rupture, like shown to the left of the screen here. And this what I call the Sumatra type, a very long rupture, and it seems like the majority of the events over the past 10,000 years and are of this type. And so so this is the most important of the message. It tends to produce very long ruptures like Sumatra subduction zone, and the recurrence time is roughly about 500 years. Okay, now we know about the earthquake occurrence in the past from local geology, from coastal geology, and offshore turbidites, and from historical records in Japan. We know it occurred in the past. We know roughly how often it occurred, and what are we doing today? So we are monitoring the megathrust today using geophysical techniques, and mainly and the most effectively using space geodesy, that is GPS, now called GNSS. And here the four red circles, and these are four continuously monitoring GPS stations, and they started operating in 1994. These four stations actually, and this is the first, the world's very first continuous GPS monitoring system in the world, the first subduction zone worldwide. And so the whole thing started here, and later on, and more and more GPS stations networks were built in the world. So this is what the configuration of our network and back then. And today we have these many continuous stations. And in addition to this, we have numerous temporary GPS sites. We go out there and make some measurements, and sometime a few months or maybe a year or two later, we go back to the same place and do another measurement. These are contained sites. And also we have numerous seismic stations to record seismic activities. So all this have provided important information and for the current locking state of the Megathrust. So what have you seen from GPS monitoring and measurements? And here, the vectors to your left, these are the velocities of the GPS stations relative to the stable North America plate. And this is the evidence for the locking of the subduction megathrust offshore here. And because the megathrust is locked and the upper plate is pushed to the east, and we have a shortening of the continental crust. The shortening can be expressed in terms of strain rates. Here, if you see a symbol of this size, and that means, and 2 points 100 kilometers apart get closer to each other by about 5 centimeters every decade. So that's over 500 years or so. That's a lot of shortening, and that shortening will be recovered in an earthquake. So this is the indication, strong indication, unambiguous indication for the locking of megathrust, just like this here. And the upper place is being shortened by the spring, accumulating energy to get ready for the next event. And so we know for sure it's being shortened like this, although we don't know exactly how complete the locking is, whether there's some creeping here and there, but we know it's at least locked to some degree. Okay, now we know the earthquake happened. Cascadia Megathrust earthquake happened 300 years ago from different types of evidence, and we also know, and the plate is locked to some degree, and after the crust being shortened this way, so we know the two end pictures now. But how do we know and how the system has evolved from this state, coseismic rupture 3 centuries ago, to the present day state like this? What is the process of the evolution process? We don't have information locally to tell to constrain this evolution. And so to understand the process, we look around the world elsewhere. If you go to Sumatra and Japan, where a giant earthquake occurred very recently, and what we see is every GPS station in the upper plate is moving towards the ocean, and just like when the way they moved at the time of the earthquake. But we go to some other places like Chile and Alaska, what we see is opposing motion of the coastal stations and inland stations. The inland stations, and they are still moving seaward, just like in Sumatra and Japan, but the coastal stations are moving landward. So we have this opposing motion. That's like a few decades after the earthquake. And Cascadia, and it is a case, and at a much longer time after a similarly giant earthquake, and here every station moves landward. So we see this a turning around of stations and gradually turning around, station turning around, and as time goes, and this whole thing can be explained and modeled using a model that involves viscoelasticity. That's the mantle part of the Earth. Upper mantle has behavior, kind of viscous behavior, and it becomes softer after an earthquake, and as time goes, it becomes softer, and it leads to a time-dependent evolution like this. So the whole thing can be modeled and explained. So by studying all these different earthquakes, we have pieced together an earthquake cycle. We can apply this cycle to the Cascadia subduction zone. Now, by doing this, now we know how our own subduction zone evolved from the cold seismic rupture to the present locking state. And now we know, and 2 years after the earthquake, well, England and France were fighting in Eastern North America, and our GPS site, today's GPS sites, and were actually moving towards the ocean. They were moving west, just like what is happening in Japan and Sumatra today. A few decades after the earthquake, when the first European landed on the northwest coast of North America, that was Captain Chirkov of Russia, and if he had GPS, he would have seen opposing motion, exactly as what we are observing in Alaska and Chile today. And by the time Captain Cook sailed up and down the west coast of North America and spent some time at Nootka Sound and Vancouver Island here, and all the stations were already moving landward. And today, and these stations are moving in the same direction, but at a slower speed. And the change of speed here is also important information, and it reflects the rheology of the Earth. Okay, now we know the earthquake rupture 3 centuries ago. We know it's currently locked, and we know roughly how it evolved from rupture to the present state. So what do we expect now? Sometime between today and something like 200 years from now, and the Cascadia subduction zone will produce a megathrust rupture. When that happens, and the rupture and could start and somewhere, we don't know where exactly where. If you assume it starts somewhere off Oregon, and the rupture would proceed like that, and if you can, some of you can see the faint, fairly faint blue color here, and now at roughly at Eugene, and this is the P wave, the fastest going wave traveling from the epicenter, and by using and these waves, and scientists can design early warning system and to warn against the more damaging bigger waves yet to come. So there's effort along the coast in both Canada and US to build this kind of early warning system, to use the faster travel, less damaging waves to warn against the more damaging and the slower waves. So let's see, and if the rupture continues to propagate and wave continues to propagate, and in about less than 2 hours, big shaking will occur in Portland if assume the rupture started somewhere in the south, and if let's see, it continues. By the time and the big waves arrive at in Seattle, that area, you can see the shaking is much bigger here in the Seattle area than its neighboring areas. And the reason is we have a lot of sediments here. And the sediments will cause a slower seismic wave speed, and that will amplify the shaking. So the local condition, the amount of sediments, and how they amplify shaking, and this is also important subject to consider when we study earthquake hazard and risk. And we have a similar situation in Canada, in the Georgia Basin, like Richmond, that area here, and a lot of sediment that could enhance shaking. And let's just let it go. And by the time, it'll take about 3 minutes and to reach Victoria. And so if the earthquake does start so far in the south, and we can design some kind of warning system, especially with seafloor monitoring, and to warn, to provide some warning for people elsewhere in the coast. Of course, the earthquake may start offshore, then we have very little warning time. People in the south have more time. As the rupture proceeds, and we'll have various hazards, and of course ground shaking that could cause building collapse, and there could be landslides, and there could be liquefaction because sediments saturated with water under shaking may behave like a fluid and like a liquid and cause different damage. So how do we prevent these kind of damage? And we do scientific research, and we assess hazards, and we produce maps like this, hazard maps like this. This is a map for the US, and this is for Canada. And they both feature very high, much higher hazard here, higher hazard, stronger shaking on the West Coast. And partly because of Cascadia subduction zone. And this information, based on scientific research, provides input for our building code, and the building code set up construction standards and to protect buildings against strong seismic shaking. And I think the audience of this webinar and people like you and will help society and to make the environment, our built environment, strong enough and to prevent collapse during earthquake shaking. So besides shaking and for subduction earthquake, we should remember another very important hazard is tsunami. And tsunami could occur along the whole subduction zone, and it can cause a lot of damage. And just like what happened recently in Sumatra and around Indian Ocean and North Japan. When an earthquake occurs, it'll take about 10 minutes for the tsunami waves to reach some places that the coastline that is not too far from the trench or our deformation front, and by 20 minutes, and many places along the coast will be inundated, like including part of west coast of Vancouver Island, and many places in Oregon and Northern California. It will take about an hour and a half for the wave to travel through the Juan Strait to reach Victoria. So the difference between tsunami hazard from earthquake hazard is there's usually some time to escape. So it's important, unlike earthquakes, we have to pay great attention to the strength of building against shaking. But in the case of tsunami, we can also design evacuation route. It's very important for life saving. So when people feel strong shaking and long enough duration, and they're pretty sure this likely a subduction earthquake, and it could be followed by a tsunami. And if they know exactly where to go, and life can be saved. And the sign here is from Bend, Oregon, and the location of this sign and many signs in this area is based on a study like this. And here, scientists use some realistic assumed rupture scenarios to do tsunami modeling and to predict the inundation scenarios. And here, different sizes and are for different people in society, and they have different purposes, and they need to know what kind of wave height and for their type of mitigation strategy. If it's for life saving, you assume the worst scenario. If it's for a certain kind of infrastructure, you assume another scenario. And this is for the application of this kind of research. And if there is nowhere to go, and very often, and it's very popular in Japan, and also I think now also great attention has been paid along this coast, is a vertical evacuation, and we can build some strong buildings, and people can climb up those buildings and to prevent to stay away from the big tsunami waves. Okay, so we have learned about the history of Cascadia earthquakes, and we know what to do, but we still have a lot of challenges, scientific challenges. And the study of earthquake hazard and tsunami hazard is somewhat different from some other types of science. For some scientific research, and the application can wait until some time later. You have some discovery, but you don't see the industrial application until maybe a few decades later. But it's not for a hazard study. And here, well, we produce new scientific results, and our clients, society, they need to use the knowledge right away. And so we are always faced with the dilemma. We know our findings have uncertainties, but we always have to try to use our best knowledge to provide and information for society, for our users. At the same time, we have to tell them, and we have more to do. We have uncertainties, and the and people and who use the information and need to understand. I think they do understand, and there's a lot of uncertainties, and there's never a time that we can say Cascadia research is over. There's always new challenges, and today I tell you all about the earthquakes, and next year I may have updated information and to improve our understanding and our strategy of risk mitigation. So let me spend the last part of my webinar to talk about some of these scientific challenges. First, is the seismogenic zone fully locked? And this is the kind of the history of the development of the locking models for the Cascadia subduction zone. And earlier models were constrained by very few geodetic observations. we had some assumptions such as temperature, and when it's too hot, it cannot rupture, and that kind of information. We built models like this. And more recently, with the massive geodetic observations, especially GPS observations, people were able to invert those data to a constraint, come up with locking scenarios. But here, and the problem is these two scenarios pretty different, and it could be a lot of different scenarios in between, and they fit the observations equally well. So the problem is that there's a lot of non-uniqueness here. We know the fault is locked to some degree, but we don't really know from geodesy, geodetic observations, the degree of locking. It is fully locked like this, or it's partly locked like that. And now the current model used in Canada and US for seismic loading is this kind of model. And this model assumes a fairly shallow and narrow locked zone offshore that is fully locked. See, we do not know whether it's fully locked like this from geodesy, as you see from here, the two pictures to the right-hand side. But we still assume the narrow and shallow full locking. Why? The reason we assume the fault is the locking is shallow and narrow is because we have very warm megathrust. And as you can see from here, because of the very young slab, which is warm, incoming plate, and thick sediment cover, and the megathrust temperature reaches over 400 degrees at a 20 kilometers depth. And that is already too warm for seismic rupture. And if you assume the fault zone material is rich in quartz, which I think is generally true, especially for Cascadia. So for that reason, we have the assumption that the locking should be shallow and narrow. So it's a reasonable assumption, but it's still assumption. But why do we assume it's fully locked? The reason is, and the megathrust is very quiet in terms of producing small earthquakes. Here are the earthquakes along the offshore earthquakes greater than magnitude 3 over the past few decades. Here, only a few of them here off Oregon here, they are identified to be interplate earthquakes. That is the small earthquakes produced by the megathrust itself. And these other earthquakes are not on the interface, they are in the subducting plate. So the megathrust is very quiet. And recently there was a big project in the US called Cascadia Initiative. Under this initiative, many seafloor ocean bottom seismometers were deployed to monitor the seismicity, and it did not change the picture. The megathrust still appeared to be quiet, except locally off Oregon in that area. And for the Canadian part, and in collaboration with Japanese scientists, we had a project. We deployed ocean bottom seismometers off Vancouver Island, here, those triangles. We monitor seismicity in 2010 for 3 months, in 2012 for 9 months, and we monitor them twice, but we still detected almost no earthquakes on the megathrust. A lot of earthquakes in the dangling plate, on the some kind of transform fault here, but very few earthquakes, almost none, on the megathrust. So it's been confirmed again and again that the megathrust is very quiet. If there's some creeping and from observations elsewhere, we would expect some small earthquakes if the fault is creeping. If it produces no earthquakes, you have to assume, we tend to assume that it's fully locked. So that's why we think it's fully locked. It's still an assumption, That is a reasonable assumption. So why can't we tell the locking state directly from geodetic observations? Here's the reason. If you look at these two profiles, one features full locking, one features partial locking. Here, full locking is 100% here, offshore on the fault here, and partial locking something like a half locking here, and the blue line here, and they produce different surface velocities. This is the landward velocity along these profiles. Assume we have GPS stations, we will see this is what we will see here. And you see, even though they produce very different velocities over the locked zone here, but on land where we have GPS observations, and there's very little difference. So that's why we cannot tell them apart using GPS geodetic measurements on land. If you look at the more extreme scenario, the trench creep scenario, again, you really cannot tell the difference from land stations. However, if you have some seafloor monitoring stations, such as seafloor GPS, we could easily tell these scenarios apart. And that's why the scientific community who studies the Cascadia subduction zone is proposing seafloor geodesy. And this is one of the many plans and to deploy instruments, mainly like GPS type of instruments. And if you have this deployed, and in a few years of time, we could easily tell these two kind of scenarios apart. We can easily tell which one of them is correct. So it's very important and quite urgent to have this thing resolved using seafloor geodesy. The next challenge is about intraseismic stress relaxation. And now we know, we've known for a long time, the Earth is not purely elastic. And the deeper part, especially the upper mantle, has a viscoelastic behavior. So when you have earthquake, at the time of earthquake, the material behaves like elastic material. But when the fault is locked, and gradually the behavior of the material becomes more and more viscous. It's more like a fluid. So the behavior changes with time, and that behavior and is considered in this kind of it actually is mostly responsible for this kind of time evolution of the surface deformation. However, and this kind of behavior, this kind of rheology, what we call, and it has not been considered when inverting the massive geodetic data into constraint locking. And as you can imagine, with or without considering this kind of viscoelastic behavior, and our picture of the inferred locking state and can be different. So that's something we are currently working hard to try to resolve. The next one challenge will be ETS and the seismogenic zone. ETS is episodic tremor and slip. The seismogenic zone here, what I've been talking about, is shallower here offshore, and some distance down dip, we have a patch here that slips episodically, slowly, and while producing little seismic signals called tremor, not real earthquakes, but they can be recorded by seismometers. We call them ETS. It occurs fairly regularly along Cascadia subduction zone and some other places. It's one of the most important discoveries in earthquake study over the past few decades. But what we do not know is the relation. So what happens in between? As far as we can tell, and there seems to be some kind of gap between the ETS zone and the seismogenic zone. Here is the rupture zone, or the slip zone of one of the ETS events. That was 2008. Here, the blue contours, and the red circles are the are the accompanying tremor sources. And here, the shaded area is our best rupture model for the Cascadia to our best knowledge. And it seems to be a gap. But because we have not observed a real megathrust earthquake, we don't know if the gap is really true. And however, in the Nankai subduction zone, southwest Japan, which is similar to Cascadia in many ways, we do have observations. And here the line, the purple line, is the down-dip limit of the megathrust earthquake rupture and a few decades ago. And they also have tremor. The tremor is accompanied by slow slip events, just like Cascadia. In between, there's a gap, and this gap in sometimes filled by different type of slow slip events. A slow slip that takes much longer than the ETS events to accomplish, several months or maybe years to accomplish. So there's a gap, and with this kind of different behavior, and it's observed, also observed in Mexico and other places. Even California, where the San Andreas fault is a strike slip fault, different from a subduction megathrust. Here we also have regular earthquakes, the big rupture and small seismicity, and we also have tremor. Here, red is the ending tremor, the spontaneous tremor by itself, and the green ones are tremors triggered by big earthquakes elsewhere in the world, by seismic waves. In any case, there's also a gap between the regular earthquake seismogenic zone and the tremor zone. If that tremor has the same physical reason as our tremor, and except they don't have a slip because they think the slip is probably too small to be observed geodetically. If they are the same thing, we are looking at probably the same reason for the presence of a gap, and so this a challenge that we have to address. The good news is we are making great progress in this research. Very soon, I will update you with some new findings in this front. Another challenge is about the tsunami-genic seafloor deformation. A subduction earthquake generates tsunamis in different ways. If the rupture is buried, does not break the seafloor, and it produces a rupture, deformation of the seafloor like that, and the uplift of the seafloor will produce tsunamis. And if in some cases, if there's a slate fault, and the ruptured slate fault will divert the rupture to a more vertical direction to enhance vertical deformation of the seafloor, and it'll cause bigger tsunami. And these two scenarios are currently considered in Cascadia tsunami source modeling. However, a different type of rupture, that is a trench breaching rupture, and that occurred in the Tohoku-Oki earthquake that really surprised us. And this is the type of rupture that's considered to be responsible for the devastating tsunami following this earthquake. And that's because the sloping, the horizontal motion of the sloping seafloor here can also cause a lot of raise water to cause big tsunami. So that raises a new question in whether the Cascadia megathrust can also have trench breaching rupture like this. In Japan, they have observations to constrain the geological structure, such as this. And this is seismic survey results before the earthquake. You can see this is a trench area like this, and the flat seafloor and sediment layering here. But after the earthquake, exactly the same profile. You can see the seafloor has been disturbed, and also the structure of the sediment has been disturbed. And so this is the interpretation at the bottom, and the conclusion is, and the megathrust motion here reached the trench and it moved for about 50 or more meters, and to squeeze the trench sediment to cause this kind of perturbation. So structural evidence like this, and or maybe other type of structural evidence for trench breaching, rupture, or the lack of it, and needs to be studied for Cascadia. And so far, with the many profiles, and we haven't gone very far, we see different structures in the sediment and near the deformation front, but there's no, so far there's no conclusive evidence for trench breaching rupture like Tohoku in past Cascadia earthquakes. But we still need to conduct a higher resolution study to get the picture clarified. So the last scientific challenge I will discuss is briefly is about along strike heterogeneity and earthquake recurrence behavior. And the top is the rupture scenario constraint, the latest rupture scenario for the 1700 earthquake constrained by coastal microfossil studies. Microfossils, in this case, mostly foramen, and they were used to constrain subsidence. And the subsidence pattern like this can be explained by rupture scenario like this. This scenario shows patchiness, right? And just like earthquakes elsewhere, instrumentally recorded big Megathrust earthquakes in other subduction zones elsewhere. So we always see these patches like in Chile, Sumatra, Alaska, and so it's not big surprise. But the important question is the dividing boundaries for the low slip areas, are they controlled by geology, or they're just random? If they're random, there's probably very little we can do about it. But if they are geologically controlled and they're persistent, then it can imagine it has important implications for hazard assessment and mitigation. It's quite interesting to see there's a correlation between these kind of segmentation boundaries and other type of processes. Like I mentioned the tribulite study earlier in the talk, and these lines are the rupture lengths inferred from those tribulite deposits, and they seem to have some correlation with the segmentation boundary, the patch boundary, the low slip areas of the rupture model. Also, I mentioned the ETS, and the ETS occurs along the margin, and it also have some kind of second behaviors, different places, and have a somewhat different recurrence interval or different behavior. And these boundaries seem to also have some correlation with the low slip area of the rupture scenario. That's quite interesting. And also remember, there's an area of Oregon that produced small earthquakes on the interface. Other part of the interface stays pretty quiet seismically, but except this place, or maybe it could be other places if we make more observation. But in any case, and this earthquake is proposed to be related to a subduction sea mount that keeps creeping ahead and producing small earthquakes. So that kind of geological control. So there seems to be some correlation, but we don't fully understand the meaning. But if some of these low slip areas are geologically controlled, if they're persistent, if they even creep when the rest of Megathrust is locked, that would be quite interesting, quite important information for to improve our understanding of the hazard and tsunami generation. And also, it also helps us understand the recurrence interval. For example, in the south, if this proposal that in the south there are more frequent events but smaller, And if the boundaries here are geologically controlled, certainly the recurrence interval will be, if they're persistent, then the recurrence interval will have a reason to be different. So this is something that is under investigation now. So in summary, here are some points to emphasize, a lot of points to emphasize, but I think these are all quite important. Let me just quickly summarize this. Cascadia, the subduction zone, likely has a Sumatra-type megathrust featuring straight-out ruptures, very large strike length, but moderate slip. And there's no doubt that Cascadia megathrust is personally locked to some degree. And we assume the locking is narrow and shallow. And because of the high temperature of the subduction zone in the megathrust. We also assume the locking is quite complete because of the paucity of the plate interface, the interface seismicity, the quiet interface. And these are reasonable assumptions given our knowledge, but they are still observations. The locking state is not directly observed. And so it is quite urgent to have seafloor monitoring get close to the megathrust locking, the lock zone, and to define the true locking state. Until that happens, the narrow locking and full locking, these are all reasonable assumptions. And also, new locking model involving viscoelastic rheology, what I call intraseismic stress relaxation, and needs to be developed. And also, multidisciplinary research is needed to understand the relation between the episodic tremor and slip and the seismogenic. Geophysical imaging and geological studies are needed to investigate whether the Tohoku-like trench break rupture occurs at Cascadia. That's important to understand our tsunami hazard. And also, it's important to use structural and paleoseismic research to examine and possibly persistent geologically controlled along strike heterogeneity in the seismogenic behavior. And the last part, which I did not really cover in this webinar, but it's also very important, and for hazard, to deal with hazard and risk, that is the local research is needed to study site conditions pertaining to shaking amplification, tsunami inundation, and other secondary hazards. Here is the end of my talk, and then if there are questions, I'll be happy to discuss. Thank you.
Great. Excellent. Thanks very much, Dr. Wang. Very informative presentation, and also a little bit unsettling. So we have a couple of questions online, and I'd like to invite anybody who's on the line. We have about 75 people here. So if you have questions, please feel free to submit at any time. First question online is related to the topic of locking that you discussed a fair bit. So the question specifically is, does locking mean that there is a less chance of a rupture in the very near future? And so I guess as a follow-on to that, maybe you could sort of unpack what locking means. Does it mean that there is, more chance of a larger release of energy when a earthquake does occur? So two questions: how does it affect likelihood of earthquake in the near future, and what are the sort of implications with respect to severity?
Yeah, well, thank you. Locking is the necessary condition for a rupture, right? If you have two plates that move towards relative to each other, if the interface keeps creeping, there's no locking, there's no chance of producing larger earthquakes. Right? You need to lock it for some time and to accumulate energy, and then the sudden motion, when it's suddenly unlocked, that's the rupture, produce earthquake. So no locking, no earthquake, right? And the locking behavior, it can be observed in laboratory. It just kind of fairly typical frictional behavior, what we call stick slip. They stick together for some time, and all of a sudden slip, stick again, causes earthquake cycles, right? And so it's typical behavior for many faults. So it's necessary for producing earthquakes. And so when we see a fault is locked, actually we are worried, right? And the problem is we don't know when it's going to break, right? And if earthquake just happened recently and the fault is locked now, and we can say, well, it just happened before, it will take some time for the energy to accumulate to produce the next event. So we may be a bit safer, except for aftershocks. But when the fault is already locked for a long time, such as for Cascadia, we are really worried. We worry when it's going to break. It's going to break today or for another 100, 200 years. And unfortunately, that's something we do not know. And nobody really knows when it's going to break. We just know for sure because it's locked, and it has to be unlocked sometime to break. I think that answers the question.
Yeah, yep, it does. Thanks very much. Next, so again, related to that topic, you mentioned in your presentation that there was a plan laid out in 2012 about geodesy for measuring seafloor geodesy for measuring, whether or not it's locked. Is there a plan to put that monitoring in place anytime soon?
Yeah, the map I show is one of the many plans, and the scientific community, I think is a broad recognition is very important, and not only for Cascadia and elsewhere in the world, it's just widely recognized, and the near field observation is needed. And there are many plans, and also there's a tremendous technological development to reduce the cost. And now the main difficulty is still the cost. But given that the cost is being reduced because of the technological development, and so there's hope, and some concerted effort can be made. And as we speak, another workshop is being planned to take place in Seattle to discuss how to do this kind of monitoring. And similar meetings have taken place in the past and will take place in the future. And there's a lot of talking, and also different proposals have been submitted, and either for feasibility studies or for more massive deployment. And so we are busy working on this subject. And when it's going to happen, and we'll see. We have some stations occupied, and a few of them, but it's just not enough. And we have there's a lot of stations like that of Japan. They have produced wonderful results, but so we are trying to catch up. We see if we can have enough resources and to have a monitoring network, offshore network like Japan. As you know, we have a cable monitoring system called Neptune of BC, of Vancouver Island, but that's still very limited, and we need more spatial coverage to get the whole thing better understood.
Okay, great. Thank you very much. Another question from an online participant. Could you outline a bit more the potential impacts on the east coast of Vancouver Island of a megathrust?
Yeah, the east coast, certainly the major concern is shaking, right? When the megathrust earthquake is difficult from smaller earthquakes because of rupture size. And when rupture size is large and the duration is longer, it can produce a much longer period shaking, and that longer period shaking can go quite far. And so the ground shaking and associated damage, like building collapse, landslides, and liquefaction, and I think they are all of concern. But for tsunami, of course, it's a less of a concern than the West Coast, right? Obviously, because water has to travel through the straits, Tectonophysics Strait and Georgia Strait to reach the different locations. And by the time it gets there, the waves will be smaller, and it could be locally amplified. But it takes a long time to get there, and people have time to escape. So tsunami is, compared to shaking, is less of a concern. But the shaking related hazard, and especially if your buildings are built on sediments, not the solid rocks, it could be of concern.
Okay, great. Thanks very much. Another question. The Cascadian subduction zone extends from northern California to southern British Columbia. When a subduction earthquake occurs, do we know how much of this zone will be active?
Well, for the next earthquake specific to one rupture, and we don't really know. It could rupture half of the subduction zone, could rupture a small part, produce 19.8 or 8.5. But what we see from tripartite studies, like the history of this subduction zone, and long history, and we see a tendency for very long rupture. So in terms of probability, and I would say the probability is probably quite high for very long rupture, but certainly not just probability. There's no guarantee. Every time, rupture the whole margin, right? So I think that's the answer is we need to prepare for whole margin rupture, even though smaller ruptures can also occur.
Right, okay. A further question, how does the risk of seismic damage from a subduction earthquake differ in British Columbia relative to that in Washington and Portland?
I don't think there's really a fundamental difference. I think they are quite similar. And the difference, instead of between British Columbia and other states, is more like between whether you have a lot of sediment or you have no sediment, but basically it's a solid rock. So locally within British Columbia, within each state. So that's a major difference. Also and also depends on the population of the coast. If you have a population center near the coast, then you worry more about the tsunami inundation. Otherwise, you worry less. I think that's the difference.
Okay, thanks again. Further question from a online participant: is there any difference between the Geological Survey of Canada and the U.S. Geological Survey views on the Cascadia subduction zone?
There's the two organizations collaborate a lot on this research, and we don't see a lot of difference. And collectively, individual scientists may have different views on specific aspects, but overall, I think the whole scientific community, because we debate, we collaborate a lot. If there's differences, we discuss, and so normally there's kind of consensus, but specific issues can be different. But this difference is more between individual scientists than between organizations. Okay,
great, thanks. A question about, so you mentioned earlier in the presentation how P waves can be used to give some advance warning about more severe shaking that might be coming along. Can you give a little bit more information about how they are used or could be used? How far in advance of a warning do they provide? for example, and then how is it actually applied on the ground?
Yeah, this is called the early warning system. It's different from prediction. Prediction is something we don't perceive here in Canada. Prediction is something about telling the occurrence of earthquakes before it happens. Right? And early warning is the warning after earthquake has already started. Right? When the P wave comes, and by analyzing this, recording P waves, we analyze them, we predict and how large the following S wave and the more damaging waves will be. And that's it's called early warning system, and it's in use in various places, and it was actually quite successfully used during the Tohoku-Oki earthquake in Japan. And by the time of earthquake, and the high-speed trains were automatically stopped, and the nuclear reactors were automatically shut off, and so it was quite effective. But of course, all know the Fukushima disaster. That was a different reason. It's not just it wasn't because the early warning didn't work. So it works, and to protect the important critical structure and facilities. And if for North America, there's a great push in California and also the western states and British Columbia, and to establish early warning system. And various testing little small networks, they are in place, and the different people, different groups are working on it. But we don't yet have a coherent, a big system to work. But people are working on it. But someday, I think it will happen. And the difficulty for Canada is we have a very large area, large land, and relatively sparse population centers. So unlike in Japan, you build a system to warn against every earthquake. Every type of earthquake. But here, we simply, it's difficult to target every type of earthquake. So the current plan is we probably can build a system just focusing on the Megathrust earthquake. If you know where the source roughly is, we can design a network wisely to warn against this type of event. But in California, it can be different. But so different people, research communities in different areas are trying to come up with the best scenarios to build a system like that.
Okay, great, thanks. I think this probably is our last question. So one last question. It gets into the topic of locking again. So is it possible that we could experience a subduction quake that's of a lower magnitude that, say, would release some of the energy and then sort of a series of lower magnitude earthquakes, or when it does occur, will it be just a very large earthquake?
That's an interesting question. Yeah, well, indeed, if you look around the world, there are subduction zones, and that like Cascadia or like Tohoku, and that tend to produce large earthquakes, or either locked or big earthquake. There are also another N number and subduction zones that just simply creep and produce a lot of small earthquakes, a lot of A-seismic slip. And in those places, you can see from geodetic monitoring, and there's not a lot of logging, and so we don't expect huge earthquakes. And but for there are also intermediate cases that the places up to like something like 8.5, and here, like Mexico, right? 97 here, 96 there, and a lot of them. But we haven't seen a really huge one like 99. And again, for Cascadia, as far as we can tell from past record from tsunami studies, and it seems to be a tendency for very large rupture, and there could be smaller events. Well, like each rupture may not rupture the full margin, right? But there's tendency for large rupture, but for many more, a series of small ruptures to release the kind of released energy to kind of preempt the big event. And that scenario, there seems to be no a strong argument for it, for Cascadia, based on what we observed and what we learned from the past. But that's something certainly to it's interesting to consider, but it's probably not very likely for Cascadia.
Okay, excellent. Thank you very much. So that this is the end of the question period. I thought I'd invite Dr. Wang if you have any concluding remarks.
Well, thank you very much, Dan, and thank you the audience for listening to me. I'm happy to provide some information on this very special day. And if you have any questions, please feel free to either check the website or contact me or my colleagues, and we will be happy to work with you to reduce the hazard and mitigate the risk. Thank you.
Excellent. Thank you very much, Dr. Wang. And thanks again for the very informative webinar. To those of you still on the line, just a reminder that our next webinar is on February 17th, and that'll be Lynn Johnson from the Canadian Forest Service talking about her project producing national wildland urban interface maps to help us identify areas of the country that are vulnerable to wildland fire disasters. And with that, this concludes the webinar. And just a reminder again that this webinar will be posted on YouTube within the next couple of days, and you can reach our YouTube site via our main website. Just click on the YouTube button. Thanks again.